All right, so at the very end of yesterday's class, we got to talking about this disk method or washer method. And we talked about how it was really a situation of two donuts, right? We have our regular donut that sort of has this hole missing. And then we have a sort of filled donut situation where there's no hole in the middle that's been scooped out. And depending on the situation, if we had a filled donut, we could use the regular circle equation for area. Area equals pi r squared. Whereas if we had a regular donut, we needed to take sort of the big circle and subtract out that smaller circle. And so our fancy way of notating that is saying pi big R squared minus pi little r squared. But knowing that we're sort of preparing ourselves to take an integral, we wanted to bump all the constants out to the front. And so we brought this pi out to the front as a greatest common factor. And then we would have our big R squared minus little r squared. Okay. We then talked a little bit about this idea of a solid of revolution and how sometimes we have, instead of cross sections like we had in the previous one that already existed, we sort of create these cross sections. And so they have this axis of revolution, and we take one of our rectangles from our area, and we spin this rectangle around the axis of revolution, and we see that it becomes a disk. Okay, in this case, we do have a filled donut situation because this radius goes all the way down to the axis of revolution. Okay. But before we go too much further, maybe let's imagine for ourselves, what if I had this axis of revolution and I had a tiny rectangle up there. And I took this rectangle and I revolved it around the axis of revolution. Would I end up with a filled donut or a regular donut? And I see here that we have a torus, and that is almost correct. In our case, I know I've been using this word donut. We're almost imagining, though, that the edges of this are not necessarily rounded. And so if we revolve this around, we'll find out that we almost have something like this. All right, and that is sort of the slice. There is a half a donut coming out of the screen at you. And then there's another half that's kind of going into the screen. Yeah, exactly. It's not a curved disc, but it is flat. I know that's such a small difference, but yes. Okay. And so one thing to keep in mind here is if our rectangle touches our axis of revolution, we're going to end up with a disk. Whereas if our rectangle does not touch the axis of revolution, we'll end up with a washer. Okay, so two different scenarios that we're going to be visualizing here. I hope that that video that I had you watch yesterday was helpful in terms of the animation, because like I said, today we're looking at some very static pictures that are just there, and we have to sort of connect the dots ourselves, so to speak. And I know that can be really difficult. And so sometimes watching technology do that instead is actually a nice stepping stone to that understanding. All right, so question number 6 says, determine the volume of the solid obtained by rotating the region bounded by x squared minus 4x plus 5 and the x-axis from 1 to 4 about the x-axis. And so let's make sure that we are unpacking what is said here, okay? So we have this function, y equals x squared minus 4x plus 5. And that corresponds to this red curve right here. Okay. Now we know that x squared is a parabola and it's facing up. We only have part of it because we have a starting and a stopping point, okay? And in particular, choose a different color. In particular, this 1 to 4 tells us that we're going to be starting at 1 and we're going to be ending at 4. Okay, starting at 1 and ending at 4. And that's why we don't have like a full-on parabola here, but we only have part of it. Okay. Now, the second curve that we want to consider here is that we actually have the region bounded between this parabola and the x-axis, meaning this is the bottom of our shape. Okay, so we're going to take this shape and we're going to revolve it. Now, a good question we should always ask ourselves is, what are we revolving around? Okay, and I want to say for our class, we're going to be focusing around things where we're revolving around one of the axes, either the x-axis or the y-axis. And in this case, we are revolving around the x-axis. So I'm going to go ahead and highlight that in here, that yellow line is my axis of revolution. Okay, axis of revolution. And so yesterday, when we were drawing our shapes for the cross sections, I said, there's this purple line I want you to draw, and I want you to tell me what that line stands for so that we can prepare ourselves for a given equation that we might need, okay? And so if I were to draw a purple line like this, okay, what does that line represent?
Is it the radius of that shape at that point?
It's exactly what that stands for, okay? So these purple lines here are going to stand for a radius, right? In fact, it is a radius of a circle, okay? It's a radius of a circle. It is not the diameter, because it isn't that I have like sort of semicircles coming out like that, right? I don't have semicircles, but rather I'm taking this purple line and I'm rotating it around the x-axis. And we can see here, like if I look at 2 on these fancy 3D diagrams, right? That right there, that purple line is the same as the purple line I just drew. And that represents the radius of the circle at x equals 2. Okay. If I drew another line, let's say over at 3, okay, that would represent the radius of the circle at 3. And we can almost look at this diagram down here, the second one, and notice that that purple line is the same as the second purple line I drew. And we can see here that they've actually drawn in the whole circle for us. All right. And so if we imagine all of these circles, we might be able to say that the smallest circle is right around x equals 2, right? Where's the biggest circle in this picture? At x equals 4. Good, good. And I would say that there, where might there be 2 circles that are the same size? There's a lot of answers to this one, but where might be brief circles that are the same size? Yeah, it looks like maybe at 1 and 3, those heights look to be the same, which means that the radius of those circles is the same, okay? Now, I know when we look at this picture, there are no circles here, Okay, I know that's like a weird thing to think about, but remember, we're not trying to be super fancy artists here. We're just trying to sort of visualize things in our head. Okay, so this is a radius. I spin it around and I end up with this circle at the end. Okay, this is a radius, and when I spin it around, I end up with this circle. This is a very large radius, and when I spin it around my axis of revolution, I end up with this really large circle down here. Okay. Now, one question that we should sort of attack now is, if we know this is a radius of a circle, okay, do all of my purple lines touch my axis of revolution? Yeah, no matter where I draw them, I could draw one here, I could draw one here. All of these purple lines are going to touch the axis of revolution. And so that actually helps us make a second decision. Are we using area equals pi r squared, or are we using area equals pi big R squared minus little r squared? Okay. Anytime we have every purple line touches that axis of revolution, we're going to have something like this, where we have a very solid shape. Okay, there's no holes in it. Solid. And if it's solid, that means that we are not going to subtract away any pieces because there's nothing missing, but rather we're going to say we want to use this area formula. Okay, area equals pi r squared. Now, yesterday, we looked at some of the shapes for triangles, rectangles, squares, semicircles. And so for every different one, we had a different equation. But here, if I'm revolving something around an axis, it's always going to be round, which means we'll always end up with a circle. Okay, so we're not choosing a different area equation here, because we can take this shape and we can slice it into a lot of different circles. Okay. Now, one way to kind of imagine this is if you've been to a grocery store that has a deli. Anybody been to a grocery store that has a deli? Like, there's a section where they sell like ham and turkey and cheese. And if you're a sandwich eater with meat, you can go there. And so when you order at the deli counter, so you say like, oh, I would like a half a pound of ham, and they take like the block of ham, right? So I think ham is usually square or something, whatever it is. And they put it through the meat slicer and it slices it into a bunch of different slices, but all of the slices are the same shape, right? And maybe you're like, oh, I like ham, but I also like turkey. I feel like turkey is sort of like the round one, right? They take the round turkey loaf thing and they put it in the slicer and they give you slices. And all of those slices are going to be circles, right? And so what we're doing here is sort of like making deli meat or making a log of cheese, in the sense that we have this function, right? We revolve it, we end up with this three-dimensional thing. But how do we find that volume? Well, we imagine that we take an infinite number of slices, we find the area of every single slice, and then we add them together. And that's why we get to use our integral notation here, okay? Now, here's what I want to do before we write our equation, okay? So yesterday we said, if we don't know where to start, it's probably a good idea to start with area equals, or volume equals the integral of area. And then it's also important as a sort of first step to say, are we choosing dx or dy? And so based on the pictures that we've seen here, what are our instincts telling us? And if your instincts haven't kicked in yet, it would be important to read in the chat or listen to what other people are saying, okay? Yeah, we have this starting point at 1. 1 is an x value. We have an ending point at 4. 4 is an x value. Okay. And we are adding all of our circles. We are stacking them along the x-axis. Okay. Now I see someone has put in the chat the x-axis. And I want to just clarify that a little bit, because tomorrow, all right, of course, on the very last day of class, we're going to see a different case where sometimes the axis doesn't tell us what we need to know. Okay, so we need to be really thoughtful about what we're drawing and the direction in which things are stacking. Okay. And so in this case, we are using dx, but I want to really be specific and say, because we're stacking our circles along the x-axis. Okay. So we know that we're going to use dx. That means we can already put in our bounds, right? We're starting at 1. We're ending at 4. And the area formula we want to use here is pi times the radius squared dx. Okay. So the last thing we need to do as part of our setup is we need to make sure we know what the equation is for the radius. All right, we need to know what the equation is. Now, I really want us to use some numbers here to our advantage, okay? And so here's what I mean by the numbers. We're gonna go back into the diagram, and I'm gonna see if you can help me figure out what the radius is at different x values, okay? So earlier I said, I want you to look at the diagram and tell me where the biggest radius is. And someone said that the biggest radius was at 4, x equals 4. What is the radius at x equals 4? Like, give me the number. Yeah, I would say about 5 is a good guess. Okay. What would you say the radius at 2 is? Yeah, I would say maybe about 1. Okay, what about the radius at x equals 1? Yeah, somewhere about 2. Okay. So if you don't know where to find your equation, a good place to start is to just get some numbers going and see if you can use the numbers to find a pattern. Okay. Now you'll notice the radius is always changing, right? Sometimes it's 5, sometimes it's 1, sometimes it's 2, sometimes it's any of those numbers in between. But another way that we could say 5, right, is I could actually say that this is f of 4. If I take 4 and I plug it into the function, that red function, that will give me the y value at 4 is going to be 5. Okay, what happens? All right, let's do a little bit of mental math. Let's take this equation, y equals x squared minus 4x plus 5. And I want you to plug in 1 for me and tell me what you get. All right, when you plug 1 to that equation, what do you get? Yeah, we get 2. Well, maybe that means that another way of saying the radius at x equals 1 is 2 is saying f of 1 equals 2. All right. Knowing that, how might I rewrite the radius at x equals 2 as 1? How might I write that using more general notation, not just a number, but like some more general notation?
The function, I mean, equation equals to 2.
We could say, whoops, we could say f of 2 is 1. Okay. So here's the beautiful thing. I'll add this maybe over here. Okay. The radius, in this case, the radius of any single circle, we can say is f of x. Whatever the f of x function is, whatever the function is that defines the red curve, that's going to tell us what the radius is of every single slice, right? We found the radius at 4. We found the radius at 2. We found the radius at 1. But if we wanted to find all of them, because there's like an infinite number between 1 and 4, I could have 1.00001, 1.01, 1.1, 1.2, 1.3. I could have an infinite number. I don't want to sit and count them all, but this function tells me what every single one of those radii is going to be. And so what we do is we make that as part of our equation, all right? So I'm going to bring the pi out to the front. 1 to 4, the radius is going to be x squared minus 4x plus 5 squared dx. So this radius is defined by this equation. All right, so we are going to go ahead and move a little bit further in terms of the computations, but how are we feeling about the setup here? That is the most important thing. All right, so I'm going to write a few incorrect answers here. Okay, I'm going to write a few incorrect answers. And I want you to tell me why things are incorrect. All right, so here's incorrect answer number 1. What is wrong with that? How did that person get that? Yeah, they didn't FOIL, but specifically, what did they do? What was the mistake or the glitch in the brain? Yeah, they just took that square power and they just said, oh, I'll just distribute it to every single term. Okay, so they just squared every single term. They did not FOIL, which means they did not distribute properly. Okay, that's one common mistake. Another common mistake I've seen is this. What happened there? Yeah, well, we need 2 of those, right? So here's what I think went wrong when I see this kind of answer. I see someone who has said, I really need to find out what this function is, and I'm just going to plug the function in, but they forgot that the equation they're plugging it into is pi r squared. Okay, and so the way that I write this step right here, how I write the formula and then I literally plug in what I need to without trying to distribute first, this has saved me a lot of heartache in terms of, okay, I do need to square this. And so it reminds me of what I need to do to that particular, to that particular term, okay? So we don't want to do any of those, right? We want to look at those, judge those people harshly because they're not us, right? We are much more masterful than that. But in fact, what we do want to do is go ahead and FOIL things out, okay? So we leave a note for ourselves that we want to FOIL. And when we do that, let's see, we end up with x to the fourth minus 8x cubed plus 26x squared minus 40x plus 25 dx. That should be correct. So give you a few moments to maybe finish foiling that out. And see if we can confirm that. You know, my computations have not been necessarily perfect lately, so I would like some confirmation before we move on. All right, good. All right, so the actual integral, power rule, power rule, power rule, power rule, power rule, right? We don't usually need a lot of the fancier types, lots and lots of power rule, okay? And we're going to plug in 1, we're going to plug in 4, we're going to subtract, all right? We should, I believe, end up with 78 pi over 5. Okay. It is a lot of numbers. I agree, okay? It is a lot of numbers. But that's why when we're looking at these, again, so much of our work, so much of our ink, so much of our brain power really should be in the setup, right? Because so much of the time we're going to have technology in a lot of these, a lot more complicated problems in like future math classes. You'll have technology that'll compute these things for you. But what you need to do is you need to go ahead and be able to interpret that. Okay, so the interpretation piece is really what makes a good mathematician a great mathematician. Okay. All right, so that is our first taste of something that is a our volume of revolution, right? We're taking something, we're creating it to be in 3-dimension, and then we're able to find the volume of that shape, okay? And so notice that this axis of revolution happens to be the x-axis. Now, before we move on, I'm wondering if you can tell me, what is the relationship between the axis of revolution and any one of the radii that we have? Like geometrically, how are those two related? Right, so we have our axis of revolution, and every one of our radii are definitely perpendicular to the axis of revolution. Okay, so we're going to leave that right here as a note for ourselves, which is radii are perpendicular to axis of revolution. Okay, radii are perpendicular to the axis of revolution. But I don't want to generalize that yet. I want to do a few more examples and make sure that that's true before we say this is true for everything. Okay. All right, so let's go ahead and take a look at example 7. All right, example 7 says, determine the volume of the solid obtained by rotating the region bounded by y equals x square root of x. So that is the graph in the blue here. And the y-axis, So we want to make sure, what color did I use last time? So we have the y-axis, and we're going from 0 to 3, and we're revolving it around the y-axis, all right? Now, a lot of times the way we notate this is we draw like a little arrow like this to show which our axis we're revolving around. And so I'll go ahead and highlight this right here. Okay, that is our axis of revolution. We've got our square root function right here. Now, how did I know that I was supposed to stop at y=3? Because that wasn't like one of the equations we were given. So I'm wondering if you can tell me, how did we know we were supposed to stop at x=3, y=3? Yeah, the bounds, right? The bounds tell us information as well. And sometimes we sort of forget about that, or we just, think it's less important than the equations that are given, but a lot of times they actually tell us where we're supposed to start and stop. And so in particular, in this question, we're going to be stopping up here, but we started counting down here. Now, if we imagine what this looks like, if we revolve it around the y-axis, we're taking this and we're sort of revolving it this way. We're going to end up with something kind of like that. Okay. Now, clearly the scale on this diagram is a little different than the scale below, but we basically have like a funnel situation. Okay. And if we look, that is precisely what they give us in that three-dimensional shape. Okay. And they even show us a sample circle. Like, what is that? This is the same circle here. Now that means that my radius of each circle, my radius is a horizontal line. Okay. So in particular, this radius is the same as this one. And it's the same as this one. So this line that they give us right here, it is the radius of a circle. It is not the diameter of the circle. But I am wondering if you can tell me whether I should use pi r squared or pi big R squared minus little r squared. The first one. Okay, because when we look at this funnel, it's solid, right? All of this is filled with the volume, right? And if we do a quick visual, any purple line that we draw is going to touch the axis of revolution. There's no hole. So we're not going to choose the one where we have to subtract something else, but rather we're going to choose the one where it reflects that it is a solid situation. Okay. So I'm wondering now if we can start to think about an equation. So we're going to need an equation to plug in for R, right? We need something to say, this is how we find the radius. And so what I'd like us to think about is maybe what some of these values are. Okay, so in particular, let's say, let's pick the top circle. Oops. So the very, very top circle, okay, at y=3, what is the radius? All right, at y=3, the radius is 9, okay. At y=2, what is the radius? Competing answers here. Do we think 6? Do we think 4? And if you're not sure, maybe we look at the more accurate picture right here, right? Sometimes the scale is a little bit easier to see. All right, now I get why we would say 6. It kind of looks like 6 on this diagram, right? But if we go back to the one where we actually have the graph, if I draw this line across at 2 and I think about the function, it doesn't look like it's getting all the way to 6, right? It looks like it's actually getting to 4. So at 2, the radius is 4. What do we think at y equals 1? That's like the little one down here. Or maybe if we think about it on the big diagram up here, what do we think the radius is there? Yeah, radius equals 1. Okay. Can someone tell me what they think the equation is for the radius? Like I take a y value, I have y equals 3, I get a radius of 9. Y equals 2, I get a radius of 4. Y equals 1, I get a radius of 1. How do I get that radius from my y value? Ooh, x equals y squared. Okay, well, let's try that out. 3 squared gives me 9. That looks good. 2 squared gives me 4. That works out. 1 squared gives me 1. That also works out. Okay. The pattern here at some value of y, okay, at some value of y, the radius equals the y value squared. Okay, the radius equals the y value squared. Well, how was I supposed to get that from the information, right? Because that seems like a really big jump. Like some of us might feel really confident in finding patterns, right? And that is an excellent strength to have. But exactly. Okay. Now let's sort of rewind maybe about 10 minutes in this conversation. When I had just drawn these pictures and I drew my lines this way, your gut was maybe saying, these are stacking along the y-axis. So I might need to have dy. Okay, maybe you were saying that, or maybe now that you hear me saying it, you're like, oh yeah, that makes sense. Okay. But if I want to have an integral dy, I have to have my equations be x equals, right? And in fact, if we use the equation that they give us, y equals the square root of x, and I want to get x by itself, I square the left-hand side, I square the right-hand side, x equals y squared. Is another way of thinking about how this pattern of radius equals y value squared came to be. So there's a few different ways to kind of approach things. Some of us are very visual. We'll be able to draw pictures and make sense of what all the numbers where they come from. Some of us are very good at identifying patterns that we find. If we have numbers, how do we find the pattern that works between them? That's a great strength to have. And some of us are really good algebraically. We might realize, oh, we need to use dy. So in order to use dy, I have to do something with this equation. I have to get it to be x equals. All right. So I say this because we all have different strengths, and accessing these problems is all about finding your strength and how you can use that to answer the question. Okay. And so let's actually get to the equation writing, right? We're finding the volume. So we want to say volume equals the integral of area. I know we've already talked about this, but I wanted to write out the same old choices, dx or dy, so that we're aware that's a choice we make every time. Okay. Now, if I'm integrating with respect to y, that means that my bounds should be y values, right? And in fact, I'm going to start with the tiny, tiny circle down here. I'm going to keep adding, I'm going to keep adding, I'm going to keep adding, but I'm going to stop when y equals 3. And so those numbers correspond to our bounds. I like to write out my equation so that I know what I'm substituting into. Okay. This radius is defined as y squared, right? So y squared is the radius. What mistake did I just make? Yeah, it should be the radius needs to be squared. Yes, okay, and thank you for saying that. The radius needs to be squared even if the equation has a square in it, because all we're doing in this step is we're saying radius is equal to y squared. But we still need all the other parts of the equation. We still need the pi, right? The pi doesn't go away. We still need the squared. And so if I do not write that, I'm going to get a very different answer, because now I'm just saying pi r, not pi r squared. Okay. So I wanted to point that out because it is a very common mistake. We fall into this trap where we say, oh, I already saw a squared. I must have already taken care of that. But you want to make sure you've got every single piece of that equation still there. Okay. Now we can simplify pi integral from 0 to 3, y to the 4th dy. I think this one will work out not too badly, right? Pi times y to the 5th over 5. We're going to plug in 3. We're going to plug in 0. That's going to give us 3 to the 5th over 5 minus 0 to the 5th over 5. And so we'll end up with, let's see, 3 to the 4th is 81, 3 to the 5th is 243 pi over 5. All right. So there is the entire question on one screen for you. All right. So this integral, not as bad as the first one, right? The first one was very long and we had so many terms and so many numbers, as Abby so eloquently put it, right? So many numbers. This one was a little bit more reasonable, but the structure, the underlying structure is still the same. We need to be able to decide, are we doing dx or dy? We need to be able to decide what is our area equation we're going to use. And we need to be able to write the radius in terms of the equations that we're given. Okay, so lots and lots of setup. All right, before we move on to example 8, I want to do one quick check. And that is, in example 6, I had asked us to write this down. The radii are perpendicular to the axis of revolution, right? We had these purple lines, and every single one of those purple lines was perpendicular to the axis of revolution. And so I want to see if that's still true in example 7. Okay. So here's my axis of revolution. Are all of the radii perpendicular to that axis of revolution? Yeah, they sure are. Okay, so let's write that down again, that the radii are perpendicular to the axis of revolution. Okay. I know sometimes it feels like Judy makes us write down these things that are like so obvious. And obviously they're true for all the ones that we've seen. But as we are sort of graduating to be, very fancy mathematicians who are ready for Calc 2, we have to learn to hone that ability for ourselves, right? What are the patterns that we see, even if that instructor doesn't tell us it's a pattern, right? So what is this pattern? Because sometimes the pattern might be different, and we need to be really, if we don't recognize what the pattern was to begin with, how are we going to know if it's different? Okay. And so that's really where I'm headed with that. And I think that'll actually pay off for us tomorrow. Okay. So before we go on break, let's go ahead and do example 8. We'll go ahead and set that up and then take a break. Okay. So this no longer has the visual, right? It doesn't have the fancy diagrams in 3-dimension. It does not have even a graph provided for us. And so this is the kind of question where we really get to start from scratch, right? Here is how we can construct a diagram. Here is how we can use our diagram to figure out what our equation for the radius is. Here's how we can tell what our bounds should be. All right, so we're really now building the question from the ground up, or building that solution from the ground up. Okay, so example 8 says determine the volume of the solid obtained from rotating the region bounded by y equals 1 over x and the y-axis from 1 to 3, and we are revolving about the y-axis. Okay. Now I wanted to throw in that 1 over x graph because I know we're good with parabolas, right? But depending on who your previous instructors are, you may or may not have a good sense of what a lot of the other graphs look like. And 1 over x is a super, super common one. And so I want that to sort of start to get in our brains in terms of, oh, this is like a nice graph, right? This is a nice graph. And so, how do we know? How do people who just look at 1 over x know what it looks like? I want us to be one of those people, okay? And so let's go ahead and start with our diagram. All right. And while I'm sketching out this grid, all right, so we've got our xy, and we look at this equation, y equals 1 over x. I'm going to draw a small sketch of it in the corner here. But in general, y equals 1 over x looks something like this. There's like one branch in this top left corner, top right corner. There's another branch in the bottom left corner. Okay. What makes this graph so special? There is a horizontal, oh, that's aggressively large. There is a horizontal asymptote as well as a vertical asymptote. And so that falls into a category of functions that might have one or both of those. Okay. So if we sort of use that over here, all right, what we're going to do is we're going to draw the branch that corresponds to where the y values might be from 1 to 3. That's only going to be the top right branch, okay? And so if I go ahead and draw that top right branch, I'm going to have something kind of like that, right? So it's about knowing your graphs, but also being able to interpret it and say, well, this is the only part that I need of the graph, okay? And it's okay if you're like, well, I drew both parts and then I realized as I went on, I didn't need that part. You can go ahead and erase that part and that's fine. That's part of the process, okay? Now we're taking this and we're revolving it around, oh, now it's small. We are revolving it around this axis of revolution. And so one of the things that I like to do, because I'm not going to sit here and draw a very fancy 3-dimensional diagram, is I take what I have and I sort of reflect it over the axis of revolution. Okay. And so here's what I mean by that. This, if I revolve it, will end up having sort of a corresponding piece on that other side. And if that's hard to visualize, maybe we sort of go back to one of the other graphs, the funnel one in particular, I think was actually quite nice to look at this way. Right? Earlier, I said, well, here's the piece that I have. And so if I want to imagine what the whole thing looks like, I sort of just drew the reflection on the other side. Right? I know the scale is different, so it looks like a wider, fatter funnel than the actual pictures below, but that's just a scale issue, right? The general shape is still the same. And so even if we go back to example 6 here for a moment, right? If I take this and I draw the reflection around the x-axis, I end up with something like that. And that looks pretty similar to what I have in the 3 pictures below, right? So we don't need to be able to draw in 3 dimensions. Some of you might be very talented. That's not in my wheelhouse, right? And so what I choose to do instead is I sort of draw the reflected piece of what I see so I can get a general idea of what's going on. And to remind myself that that's actually not part of the starting function, I actually tend to do it in a dashed line. Okay. Now I do want to go ahead and put the bounds on here. All right, so we have one at y equals 1, and then we have another one at y equals 3. Okay. And so essentially what we have, I'm wondering if someone could maybe describe what they think this 3-dimensional shape actually looks like. Yeah, it kind of looks like a volcano, right? So I don't know how many of you did science fair when you were younger, or maybe you have children who are doing science fair projects, but I feel like the volcano is such a classic one. You know, you mix some household ingredients together and it sort of bubbles over in a very visually delightful way, right? But what we have here is indeed a volcano, right? Because when we revolve, we end up with a smaller circle at the top. And it turns out this time that the biggest circle is on the bottom. And we've got a bunch of circles that sort of stack up the y-axis, okay? And so if we think about this line, any of these purple lines will now be the radius of a circle. And if we wanted to get more detailed, we could even say stacking up the y-axis, right? That tells us right away that it is dy. All right, now let's play that game again of like, if this is the y value, what is the radius? Because I think that's a useful game in helping us figure out like, what is the pattern with the numbers, right? So at y equals 1, what do you think the radius is? And I know there's no markers on the x-axis, but sometimes going back to the equation is actually helpful. All right, so if we take 1, if we take 1 for y and we plug it into that equation, 1 equals 1 over x, well then the radius must be 1, right? This in particular, when I draw the line horizontal like that, that's an x value, right? It tells me how far I've gone out side to side. And if I keep playing that game and I say at y equals 2, what is the radius? At y equals 3, what is the radius, right? We might notice that we can keep plugging in numbers for y, right? But let me ask you something. If you're plugging in numbers for y here, is it easy, like, do you get your x value right away? Or do you have to do a little bit of work? Yeah, we have to do some work, right? And so maybe now is sort of the time as you're working through the problem that you're like, well, maybe let me just solve for x right here. And if we solve for x, we'll end up with x equals 1 over y. And that actually might be easier for us to now use and figure out, what is that radius? What is that radius, right? So at y equals 2, the radius is going to be 1 over 2. When we say 1/2. At y equals 3, the radius is going to be 1/3. And so we could say in general, at any y value, the radius equals 1 over that y value, okay? And this radius is an x value, okay? And so we can see that as we sort of go through these questions, there's a lot of fluidity in terms of how we make these decisions. And so whatever approach you take, I would really encourage you to be really consistent about your approach. That is, are you asking yourself the same sort of questions? Are you forcing yourself to make decisions along the way rather than just looking at what someone else did and copying those steps without really engaging in that process, okay? So once we've got our diagram and all of that information, now we're ready to set up and solve that volume integral, okay? So volume equals the integral of area. We'll include our typical dx or dy. And we have so many clues here that tell us we want to do dy, right? The bounds they gave us were y values. That's one clue. I'm stacking these circles up the y-axis. That's another clue. I could rewrite my equation so it's x equals. That's another clue, right? So many clues tell us we have the integral from 1 to 3 of pi times the radius squared dy. Okay. what equation should I use for the radius? Well, we already thought about that. And we said 1 over y will actually be sufficient to determine the radius. And so let's go ahead and make sure we're substituting in appropriately. Bring that pi out to the front. My radius is 1 over y. Well, gosh, I made that same mistake again, right? I filled in my radius and I was so excited that I had actually found an equation for that I forgot to actually square it instead. Okay, so all parts of that equation still have to be there, right? The pi still stays in both equations. The radius is now written in a different way, but we still have to square it at the end of the day. Okay. I simplify this. And you tell me, integral of 1 to 3, 1 over y squared, power rule or natural log? Power rule. Okay, how would I change this so that it had been a natural log? Yes, natural log is only for one, or when the power is -1. But check this out. Remember when I said earlier, a mistake that might happen is pi equals the pi integral from 1 to 3, and you forget to square it, right? Now your answer is going to involve a natural log, which is not what your answer should involve, right? So this is actually a really clear situation where the wrong integral setup will give you a very, very different answer, right? All right, so you're going to do the power rule. You're going to work through this. You should get 2 pi over 3. Okay. And again, the integral, not so bad. Definitely not as bad as that first question we saw. A little bit more difficult, I think, than the second question, but still overall not too many numbers, okay? Now, before we go on break, let's just think about this for a moment. Here's my axis of revolution. 2 questions I want you to ask yourself. First of all, do all of the radii touch the axis of revolution? Like every single purple line that I could possibly draw, does that touch the axis of revolution? It does, okay? Now, if every radii touches that axis of revolution, that means that it's solid. It means that there's no hole in the middle, okay? So this is almost like that volcano from that childhood science fair project, except there's no hole in the middle. It's almost like you forgot to leave the hole for your baking soda and vinegar, okay? The other question is, here's my axis of revolution. Are all of the radii perpendicular to that? Okay, that is a consistent pattern we've seen, that the radii are perpendicular to the axis of revolution. Okay, that's going to be our theme for today, but tomorrow when we do a different method, that may not be the same anymore. Okay, so as you learn rules and someone tells you this is always true, you should, as a very skeptical mathematician, be always saying, but when might it not be true? How might it not be true? Okay, so I'll tell you for today, the radii are perpendicular to the axis of revolution, but tomorrow when we draw different purple lines, this might not always be true. Okay, so this is a good start. We've gotten through 3 examples so far. We're going to go ahead and take a break right now, and then we're going to come back and look at some situations where we do, in fact, have a hole in the middle. Okay, so I'm going to stop the video right here. All right, so before break, we took a look at 3 different examples, all sort of highlighting different decisions that I want us to be thinking about. We're going to go ahead and do one more example before we move into the sort of regular donut situation, okay? And in particular, we're going to take a look at example number 9 here. So example 9, like example 8, has no fancy diagrams with it. It is something that we are expected to draw and come up with the information that we need to solve the problem from this, okay? So we're going to determine the volume of the solid obtained from rotating the region bounded by y equals x squared minus 4x and y equals 0 about the x-axis, okay? And so what we're going to go ahead and do right now is we're going to go ahead and draw a diagram. Okay. And so as I'm setting up my X and Y axes, if you could start putting into the chat what we know about the functions that we are drawing. Okay. All right, so what should I be drawing for my functions here? Yep, y equals 0 is the x-axis. Nice, nice. We do have a parabola facing up. Yep. And I think we can be even a little bit more specific. This is not shifted down 4. Okay, there's a very subtle difference here. This says x squared minus 4x, not x squared minus 4. Okay, so the fact that there's an x there actually changes what it means to have that minus 4 there. But I bet we can use some other techniques that we've learned to think about what we can do with that particular equation. Yeah, we can go ahead and factor out that x. All right, so let's go ahead and do that. Y equals x minus 4. And that minus 4 does not necessarily mean shifted to the right 4. Okay, so I want us to be really careful about these patterns here. Certain numbers do tell us things, but other numbers and variations of that don't always tell us something else. Okay, in fact, the graph transformations here are actually really hard to see, but we can graph based off of x-intercepts and see where that takes us. Okay, so there are 2 x-intercepts. What are the 2 x-intercepts that we have here? Yeah, 0 and 4. Okay, so we're going to go ahead and sketch a parabola here that goes from 0 to 4. It is indeed facing up. All right. Now, if we look at this, the reason why we can't say that this parabola is shifted to the right 4 is because it originally started at the origin and it didn't just slide over 4, right? That's not what it did. It sort of did a diagonal situation. And so that's why this minus 4x doesn't tell us it moves to the right or left, okay? It does help us find the intercepts, but it doesn't actually tell us what it's moving or how it's moving, okay? Now I have my axis of revolution. I like to sort of get that in there, all right? And what is the area that we're revolving, right? It's not all of this, but rather it's just the piece here. And so we almost have like a secret top function, if you will. That is that y equals 0. That sort of tells us what we are revolving, okay? Now, again, I sort of like to help myself visualize what's happening. So I might say that when I revolve it, I'm going to end up with sort of this other piece. And this gives me a good idea of what the cross section looks like. Okay. Now, if I were to draw a series of purple lines, each of those purple lines represents the radius of a circle. And each of these lines touches the axis of revolution. So that means that we're going to be looking at an area equals pi r squared situation. Okay. Now, I'm wondering, based off of just this part of the picture right here, can someone tell me how I might find the radius? How I might find an equation that tells me the radius of every single purple line there, or every single slice?
It's the equation, right? From 0 to 4, from 0 to 4.
Which equation?
Y equals x squared minus 4x. Right.
Okay, so this might be a good guess, right? We're thinking we might want to do dx because we're stacking along the x-axis. And our equation is already in terms of x. But that's actually not quite right. Right? For example, let's say we put 2 into the x value. What's the y value that comes out? I get a -4. Right? I put 2 in there, I get 4 squared minus 8, which is -4. Well, I know that this value is below the x-axis, but yeah, we're thinking about radius as positive. So let's kind of rewind in our brains a little bit. Let's imagine we're back in 1 dimension to 2 dimension, meaning that I want us to find the area bounded by this. How would you find the area? I mean, perhaps symmetry is useful, but I'm more interested in the equation. How do I find the area? Ah, okay. Top function minus the bottom function. Okay, what's our top function here? Okay, so in order to find our radius, sometimes we have to revisit these ideas of top minus bottom or left, right minus left, okay? Top function is 0 minus the bottom function, which is the equation we were given. What does that look like? Okay. Now, when I plug in 2, what do we get? When I plug in 2 in for the x, what do we get? Now we get a +4. And that should make a little bit more sense for us when we're thinking about finding that radius. Okay. So this is to say that even though this is a different section than 6.1, we have to use some of those decision-making skills from 6.1 to help us find equations for 6.2. Okay. And so maybe let's write a note to ourselves here that this is the top function. This is the bottom function. And that in this case, and is true when we have any sort of pair of functions that we're trying to do, we want to do top function minus the bottom function. Or if it's a dy situation, right function minus left function. Okay. Now, once we've done that, now we can set up and solve our integral. Okay. And so we can say the volume equals the integral of area. I think we are appropriately choosing dx because we're stacking our circles along the x-axis. And so we can say the integral from 0 to 4 of pi times the radius squared dx. Now I saw earlier that someone had said something about pi r squared over 2, and I'm wondering where that divided by 2 came from. All right, so just to be clear, when we're looking at this, each of these lines already represents the radius. Yeah, but that doesn't matter though. The fact that it's in the lower half, like if we look back at our other diagrams, we only have half of that diagram. But that half gives us the radius. If we had the full picture, that would be the diameter. That would be different, okay? So that is a super classic, I think, misunderstanding about what we're drawing here, but the lines that we draw, those correspond to the equations that we write for the radius. And as long as we have the radius, we can plug that right into the equation, okay? It's a little bit different than yesterday's thinking. All right, so we have our radius, right? We have our radius. And in fact, we have negative x squared plus 4x is going to go in everywhere we see a radius. Right. And so I'll go ahead and bring the pi out to the front, 0 to 4, negative x squared plus 4x, that quantity squared dx, right? I'm not going to make the same mistake I made in the previous two problems. I'm going to be really explicit in my brain about saying I have something squared. All right. Now, I know that someone else said something earlier about symmetry, right? And I do think we could use symmetry here. How might we exploit symmetry to help us keep our numbers a little bit smaller in this case? Right, this is a little trickier to see, but there is a way we can split this so that we get smaller numbers.
Is it 2 times the integral from 0 to 2?
Yeah, exactly, exactly. So we can say double from 0 to 2 of that pi radius square. Okay. The reason being, a parabola is symmetric. It is symmetric around the vertex. And it turns out that that vertex is at 2. So if I integrate from 0 to 2, I'm going to find this volume on the left-hand side. And then to find the whole volume, I can just times 2 to get the other half. Okay. So either way, you can compute. The numbers do get a little bit larger here. I want to say that this is a 512 pi over 15 situation. Okay. So here it is all on one page. I wanted to do this one last situation where we have a filled in donut, right? No inner radius to subtract, because this one had that little bit of a twist where we had to do the top function minus the bottom function, okay? So you really, really have to draw an accurate picture in order for things to sort of help with that decision making, right? If you shortchange yourself on the diagram part, you might actually be hindering your ability to write the equation later on, okay? All right, so this last part of today, we're going to take a look at the washer method, okay? So disk and washer method are basically the same method, but do you remember earlier when I said, what happened if we had a rectangle that was sort of floating, that it didn't actually touch the axis of revolution, right? And I had you imagine that, but now we actually have a diagram that shows us what happened. All right, so we can see from this diagram that we end up with sort of an inner function and an outer one. Okay, and in particular, the outer function has a radius of r, big R, and the inner function has a radius of little r. And so that is how we're going to be modifying things. We're going to draw some diagrams. We're going to have to choose dx or dy, but in addition to that, we're going to have to choose which one is the big radius and which one is the small radius, okay? So we're not just writing one equation for the radius in general now, but now we have to come up with a big radius and a small radius, okay? And so a note that we might want to make for ourselves is that capital R is the function that is further away from the axis of revolution. Okay, so the function that has a greater distance from the axis of revolution, that is your big R. Sometimes we refer to this as the outer function. Okay. Now, in contrast, we could say that little r is the function that is closer to the axis of revolution. Okay, so the function that is closer to the axis of revolution. And sometimes we refer to this one as an inner function or an inner radius. Okay. So a new layer to our decision making, right? We have some functions, we're going to have more than one though, and which one is closer to the axis of revolution and which one is further away, all right? So let's take a look at example 10. All right, so example 10, determine the volume of the solid obtained by rotating the portion of the region bounded by y equals the cubed root of x and y equals x over 4 that lies in the first quadrant about the y-axis. And so lots and lots of words here, but one of the things I like to really root myself in is like, what am I rotating around, right? And so I will go ahead and highlight that axis of revolution to bring that to my attention. Now, in all of the questions we've seen so far, we've said that the radii are perpendicular to the x or to the axis of revolution. Okay. So that means that if my axis of revolution is the y-axis, which direction should my radii be in? Vertical or horizontal? Yeah, if we have the axis of revolution that's going up and down, our radii should be going side to side. Now, you might have noticed something as soon as I started sort of drawing that in the red, like this little radii down here, this little radius, that touches my axis of revolution. Does that second radius that I just drew touch the axis of revolution? No, right? It doesn't go all the way to the yellow line. And same thing if I chose like a teeny tiny radius up here, that one does not touch the axis of revolution. Okay, so as soon as I've drawn this picture, even if I were, on a quiz or on a test and it wasn't in this section, the clues I would look for is when I draw my purple line, it does not touch my axis of revolution, not everywhere. Okay. And so to kind of help us out with this first one that is like that, I've gotten those three-dimensional pictures right here. Okay. And we can tell that this time we kind of have a funnel, except part of that funnel has been scooped out of the inside. In particular, like all of this area has been scooped out. Okay. And you can tell from here that a sample slice has a hole in it, right? This sample slice has a hole in the middle. It is like a regular donut. Now, I have the two functions here. One is in blue, one is in red. If I were to sort of draw the outside of this sample slice here, should I draw that in blue or should I draw that in red? All right, I see one vote for blue. Okay, so this is where that visualizing piece comes into play, right? This is the blue curve. And it touches sort of the outside of the shape. And so if I were to continue with the color coding, I would say that that outer function is the one that is blue. And similarly, if I look at this red one, that red one is certainly a little bit closer to that axis of revolution, right? It's got a smaller distance to the axis of revolution. So I can color code the inner ring to be red. Okay. And by doing that color coding, what I've decided is that my cube root function is the one in the red. And my x over 4 is the one in the blue. And the blue one is actually my big radius. And the red one is my small radius. Okay. In other words, big R equals x over 4, whereas little r equals the cube root of x. Now, knowing that I'm going to be taking some integrals at some point, I may just want to keep it in the back of my mind that this is like x to the 1/3. Okay. All right. Now, I also noticed that in this question, they didn't give me any bounds. They just said, take these two curves. They intersect at 2 points, but I'm not going to tell you where they intersect, right? We can see from the graph, but how is it that we find out where those intersection points are algebraically? Yeah, exactly. We're going to set those two functions equal to each other. So cube root of x equals x over 4. Okay. I'm going to go ahead and cube both sides. x equals x cubed over 64. How do I proceed from here? So we haven't really seen like a cubic function, but I bet we could extend some things that we already know how to do. All right. So I like these strategies, but I'm telling you right now, we're going to lose some solutions if we do that. All right. So I know that we have a different strategy when we think about something squared. We also want to think about a different strategy when we have something cubed. Okay. Meaning that we don't really want to divide by any variables. That's actually a really dangerous situation because when you divide by a variable, you are very likely dividing away a solution. All right. So my suggestion here would be let's multiply both sides by 64. Let's get everything to one side, set it equal to 0 and factor. Okay, just like we did with the quadratic. So we're going to get x cubed minus 64x equals 0, or x times x squared minus 64 equals 0. And now we're going to get x equals 0 as one solution and x equals plus or minus 8 as the other two solutions. Okay. So of those 3 x values, only 2 of them apply to this situation. And in particular, x equals 0 is going to be this first intersection point, and the second one is just going to be x equals positive 8. That's our second one. Okay. So we're not going to use the negative one in this case, but it is really important to consider there is a negative one as well. Like depending on where I had drawn the picture, it is possible that I could have taken sort of this region down here as well. Okay. All right, so we found our intersection points. Let's go ahead and set up our integral. So volume equals the integral of area. Now, are we thinking dx or are we thinking dy? All right, we are thinking dy. That is good. Okay. And if you're sitting here saying, I don't understand how people are getting that, I would encourage you to have conversations with each other. I know you folks talk to each other about your work, which is absolutely fine, but it's not just about like, how did you get this answer, or like, what answer did you get? But beyond that, like, why did you choose dy? Explain that to me, okay? All right, so we have our dy. That means we want to have the integral of pi, the radius, squared, squared dy. What are we going to have for our bounds? Good. I know we just found x values. And I'm so glad to see we know we can't use those x values when we're thinking dy, right? In fact, we have to find the y values that go with those. And so if we take 0 and we plug it into either the red or the blue equation, we'll get 0. But when we take 8 and we plug it into either the red or blue, we're going to get 2. And so our bounds here are y numbers and should be from 0 to 2. Okay. However, look at what I did. I just said pi radius squared, right? But we said that there's a middle part we have to scoop out. But right now my equation doesn't say scoop out that middle radius, right? So I have to modify this a little bit. I want to say big R squared minus little r squared. Okay. So I need to have my big R and my little r. All right. So here's what I'm going to do. I'm going to factor out the pi. I have an integral from 0 to 2. And earlier, I said the big R was x over 4. So x over 4 squared minus little r is the cube root of x squared dy. You should be just as uncomfortable as I am right now looking at this, being like, she just mixed up a lot of x's and y's all together, right? Because I did, and we can't do the integral that way. So how do we get the big R to be something, something, something with y's in it? And how do we get the little r to be something, something, something with y's in it? Right? That is our question, because right now, this is a y, this is a y, this is a y. So we got to fix the parts that are not y. Okay. So let's do some of that work. Let's do that off to the side. So we said y equals x over 4. That means x equals what? Good. X equals 4y. So that means that I'm going to replace x over 4 with 4y. All right, my other equation was y equals the cube root of x. What does that mean x equals? Good, I'm just going to go ahead and cube both sides. I get y cubed, and that, my friends, is going to go in for our little r. Okay. So what do we have? We have pi, the integral from 0 to 2 of 4y squared minus y cubed squared dy. We have our inner function, the one that is closer to the axis of revolution. We have our big R, or the function that is further away from the axis of revolution. Okay, so we have our blue one squared minus the red one squared. Once we've got that, you can proceed along your merry way. You can distribute, combine like terms if you have any, excuse me, integrate, and you should end up with 512 pi over 21. Now, I've had students in the past sort of say this reminds them sort of like a flower, right? You've got like this piece over here. When you draw the corresponding piece on the other side, it kind of looks something like that. Okay. All right. How we doing on example number 10? We ready to do one more? Okay. All right, so I think we're gonna finish with example number 11 today, okay? This should complete the content on quiz number 15, all right? So quiz number 15 is only on 6.1 and 6.2, which means that You should be able to finish up the quiz today if you wanted to, and therefore leaving yourself tomorrow to really focus on studying for that exam. All right. There's no quiz 16 this week, but there is one final classwork assignment at the end of the week. So make sure you do that. All right, let's go ahead and take a look at this last example. All right. So again, we're looking at ones where the pictures are included, but we want to make sure that as we are taking a look at that quiz, that we're drawing diagrams as necessary. We are showing our skeptical reader that we know where all of these pieces come from, okay? Yeah, it should be 6.1 and 6.2. Let me double check. Yeah, it should just be 6.1 and 6.2 as a typo. All fixed. Okay. All right, so let's take a look at example number 11, okay? Now, I bet we can tell from this diagram right away that no matter which axis of revolution, so y-axis or x-axis, those purple lines are only going to be sandwiched in this little like banana looking shape, but they're not actually going to touch the axis of revolution, okay? And so to begin, let's identify where that axis of revolution is. We scan through the problem. We notice that it says that it's revolved around the x-axis. And I could have also just seen the little circly arrow thing there as another clue that I was looking to have it revolve around that axis, all right? And so what does this look like? Let's maybe look at the visualization while we have it, right? I think that's a really powerful thing to think about. It looks like we have sort of a funnel situation again, but this time it's facing the other way, almost like a megaphone, something like that. Or if you've seen those old school music playing situations that has like a little horn looking thing like this, maybe that's what comes into your head, okay? But as you're looking at these shapes, try and imagine what they look like in 3D. It's such a small exercise, but a powerful one, and just helping you understand like what we're actually doing, okay? Now, before we even sort of highlight this picture right here, I'm wondering, based on this diagram, can you tell me which one is my outer radius and which one is my inner radius? Or which one is my big R and which one is my little r?
The big R 2x squared and the little one x cubed.
Good, good. So the 2x squared. Now I know that happens to also be in blue, but maybe the reason we would say is because this is our axis of revolution. Which one is further away? Well, if I go straight up from the axis of revolution, the first one I come to is going to be the smaller one. And the last one I get to, that'll be the outer one. Okay. And so we have our x cubed in for our small radius, okay? All right, now if I were to draw some of these purple lines here, the purple lines should be vertical this time so that they are perpendicular to the x-axis, right? And in fact, like this would be one, this would be one, this would be one. All right, before we move on to visualizing a little bit more and setting up the integral, I do want us to practice finding those intersections. Okay. So I think by now we know we're going to take the two equations and set them equal to each other. right? 2x squared equals x cubed. But as a follow-up to our previous question, what we don't want to do is divide by x squared, right? In fact, in general, when we see polynomials like this, we want to move everything to one side, set it equal to 0. So we have x cubed minus 2x squared equals 0. We can factor out an x squared. And then we'll get our 2 intersection points. All right. I know those are provided there, but you know why they're provided? They're provided so you have an answer key to know whether your answers are right or not. Okay, so please get in that habit of finding those intersection points. All right, a lot of this information is supportive rather than, oh, it's already there, I don't need to find it. Okay. All right, so based on the diagram and what we have so far, are we thinking dx or are we thinking dy? All of these purple lines are stacking along the x-axis, so we're thinking dx. So there's my template that I'm going to plug in all my information to. And what values can we use for our bounds here? Good, good. We want to choose those x values, right? And so in particular, the values we found here, we can actually use. I know we couldn't in the last problem because it was dy and we found x values, but since we are in dx, we can use the x values and we can say that this is 0 and this is 2. Okay. So let's see what we wrote down for our big R and our little r. We've got 2x squared and we've got x cubed, which means we can bring out the pi, the integral from 0 to 2. And we're going to have 2x squared squared minus x cubed squared dx. All right. Not a lot of extra work. Like I don't have to change it to a different variable in this case. All the stars aligned and I was able to just plug in what I have. Okay. But sometimes we need to do a little bit of work like in those other problems where we had to change it to dy or a different variable. Now I'm going to write down what the number one mistake is I see when students move past this point. Okay. There are 2 mistakes in that. What are those 2 mistakes?
The 2 and the x to the 5th.
Good. I did not square the 2, right? This squared means you square the 2 and you square the x squared. Okay, that's the first mistake. The second mistake, a power raised to a power means that I'm going to multiply those powers, right? So we can start to see how a lot of our previous knowledge, if we're not super solid on that, leads to like all kinds of mistakes here, right? And that's definitely something that as you move into Calc 2, if that is in your path, Calc 2 is so algebra heavy that this kind of stuff and these kinds of mistakes are very unforgiving. Okay, so if you're planning to take Calc 2 in the fall and you're thinking, I don't know, my algebra is not so great, I would really encourage you to spend some time just practicing exponent rules and foiling and factoring. That will take you really far in Calc 2. Okay. All right, but how about a right answer, right? We have pi, the integral from 0 to 2. We're going to have 4x to the 4th minus x to the 6th dx. All right, that's going to be a little power rule situation. And then we should end up with 256 pi over 35 as our answer. Okay, so let's get that all on one page for you. All right. Okay. So that is where I think we're going to end our story today. Okay. We've talked about a lot of different situations. All right. And I think that if your brain is feeling on overload because there's so many decisions to make, that's a really good indicator that you should not put everything down and forget about it until Thursday, but that you should sort of embrace this uncomfortableness and sit with it for a little bit, and perhaps immediately after class, if you have the time, and just kind of run through the decision making that we did. How go back over the notes. You don't even have to do a different problem. Just go back over the notes and see, why did we choose this? Why did we choose that? And go back and annotate for yourself. We did this because, and fill in the reason. Okay. So on that note, I'm going to go ahead and stop the video here.